Okay, good evening, everyone. I'm very happy to be here for the first time in this event. Thanks, Exnes, for inviting me. And today I will talk about a quite exotic topic. This is a blockchain. But first, let me briefly introduce myself. I have been working in software development for more than 20 years. Most of my career has been in telecommunication domain. And I work with such companies like Nortel, Avaya, Ericsson, Netcracker. 15 years ago, I created my own software platform for rapid development of applications. I built a fitness club management system that was widely used in Russia and CIS countries. In 2019, I founded my own startup to create a low-code platform. And this was called Craft Systems, and it was a resident of Skolkovo Innovation Center. For the last 3 years, I am the CTO of a European fintech company that issues a cryptocurrency, stablecoin named EURS. So at STASIS, we created a digital platform and created support of all crypto operations for stablecoin and made integration with 6 blockchains. And from that moment on, the obvious problem arose: how to make the EURS stablecoin seamlessly transfer between different blockchains. So why this is a problem and what have we came to after some study, I will try to explain further. So in today's talk, we will cover the following topics. Why the blockchain bridges are needed at all, what the main bridges types and the main principles of their work, the nature of interoperability trilemma, the details of atomic swap and HTLC protocol, and the explanation of EURS bridge architecture. So why bridges? In order to answer this question, we will start from blockchains. Blockchain technologies came to our life just like the internet some time before. I hope that many of you know, at least, and hear about Bitcoin or Ethereum. Now I want to ask you to raise your hands who does not know what blockchain is at all. No such people. Everyone knows what blockchain is. That's good. And please raise your hands who at least once has used the cryptocurrency wallet. Oh, so many people. I didn't expect that. That's very nice. Okay, so since inception of Bitcoin in 2009, the number of blockchains began to grow very fast. And current estimates suggest that the number of blockchains is above 1,000. The main purpose of blockchain is using a digital asset, but there are several problems preventing seamlessly move and transfer digital assets between blockchains. First problem is that due to the blockchains are self-contained system, they cannot they operate independently. They cannot interact with each other. Also, the blockchains use different and even incompatible technologies. For example, different consensus mechanisms, different design of smart contracts, different programming languages, and that's why they cannot interact easily. And also, by their design, the blockchains cannot read external data. They are just unaware of what is happening outside the blockchain domain. So in order to resolve all these problems, the bridges appeared. So they help the blockchains to interoperate. By classical definition, the blockchain bridge is a bidirectional system that transfers an information from one blockchain to another. The information could refer to the digital asset, to the contract calls, to the proof, or even state. Currently, the blockchains have become an integral part of cryptocurrency ecosystem, And for example, as of January 2024, the total value locked in all the bridges related only to Ethereum ecosystem is about 23 billions. However, the bridges also brought some security problems, and the biggest of them is loss of money. By the example, in 2022, the total money that was stolen from all the bridges is about 2 billion. Anyhow, the bridges are needed, and let's see how the bridge usually operates. Typical architecture of the bridge consists of three main components. First one is a source blockchain, then destination blockchain, and cross-chain component. The cross-chain component main function is to transfer messages or information from source chain to destination chain. And typical implementation of the bridge process goes through several steps. First step, the user transfers his funds to a custodian. Custodian immediately locks it. Then custodian sends a signal that the funds were received. The cross-chain component sees that signal and transfers to the destination chain. On a destination chain, this issuer can now unlock the assets or mint them for further usage. In the whole process, the most critical part here is getting the destination chain to accept that event on the source chain, for example, locking the assets, has happened. This is called a finality. Without a finality, we cannot guarantee that the process will be atomic, let's say so. But the finality is very difficult to implement because source and destination chain generally cannot interpret and validate the state of each other. So the most important problem here, how to pass and validate the state. So the bridges solve this problem of validation by introducing a third-party mediator. In centralized bridges, the mediator is usually some operator or a member of permission committee that can deliver messages from one chain to another. This is a trusted model because the user needs to trust this centralized party. In decentralized bridges, anyone can relay information from source to destination chain, but the participant needs to stake some capital first. And because of this capital and stake can be slashed anytime that another participant notices the fraud, then the participant is economically incentivized to act honestly. However, still this schema is not trustless because the user needs to trust that at least one actor is honest. In trustless bridges, they use cryptographic proofs in order to verify and validate the information that is passed from chain A to chain B. And usually, the security of such bridges is the same as of underlying blockchains. When we talk about interoperability, security, and the trust, the most important question is who is verifying the system and how much does it cost to corrupt it. So based on how the bridges solve this problem, we can divide them all into three big groups. First one is externally verified. In this group, usually there is a group of external validators, or we can say about the network of validator nodes that collectively monitor the source chain the source chain address of the bridge and collectively come to a consensus when an event has happened. Then they can perform some action on the destination chain. The token transfer is usually done in this model in lock and mint mode. That means that the original funds are locked in the source chain, and then on the destination chain they are unlocked, and usually this is not native tokens but derivatives or wrapped tokens. In natively verified bridges, they usually explore the idea of actors. Those actors are deployed on chain. This is usually smart contracts that look into certain transactions on the source chain And once that happens, they generate a cryptographic proof that is together with the block headers is delivered to the source, to the destination chain. On the destination chain, there is a corresponding smart contract that receives that message and verifies it. If the verification is done, it can perform some actions on the destination chain. And finally, the locally verified bridges, they usually is built as a peer-to-peer network where each node acts as a router and holds the liquidity of both source and destination chain. It's called locally verified because in the verification process, only the two parties that are actually doing the bridging involved in verification. And the verification itself is backed by the blockchain by using some lock mechanism. So it's a lot of theory already discussed, but it's very essential for choosing the right technology. Let's go further and see. Now we come to interoperability trilemma. So let's put the most important properties of the interoperability protocols to the corners of triangle. First one is generalizability. That means the capability of transferring arbitrary data from one blockchain to another. Another one is extensibility. That means that we can easily extend our protocol to any other domains. And the trustlessness is the property that actually means that the security of the protocol is the same level as of underlying blockchains, meaning that we do not need to trust anyone or any third party. So if we, so the interoperability trilemma actually says that no interop protocol can implement all of three properties. Only two is possible. Why is that? Because if you take all three properties, they all contradict to each other. They cannot be implemented together. So let's compare these properties based on verification type. So natively verified bridges are trustless because their underlying verifiers usually doing the bridging on chain, and they also allow for fully generalizable message passing. However, they cannot be easily extendable because they heavily rely on smart contract capabilities of underlying blockchains, but the blockchains in nature are very different. So that's a very difficult task. Also, externally verified bridges, they are generalizable and they are extensible. However, they are trusted, so they cannot be trustless. They need some trust from the user for the third party. And then locally verified bridges, they are also trustless because their security is backed by the underlying blockchain again. And they are easily extensible because they do not have such strong requirements for underlying smart contract capabilities. However, they are not generalizable because they cannot deliver arbitrary data. So every time this is a compromise. Okay, now enough theory, and now we are ready to design our bridge, and we need just to clarify the requirements. So first of all, for our bridge, for EURS token, we are not going to support any other tokens. It's enough for us only one token. Also, we are not going to support any other blockchains rather than those that we already support or are going to support. And because we are using the native assets on each blockchains, we will avoid a wrapped token or derivatives token. Based on the interoperability trilemma, for us is most important to have two properties, which is extensibility and trustlessness. It's not important for us to have generalizability because we are going to support only one token and only supported blockchains. However, to implement trustlessness, it's quite difficult because even the supported blockchains are heterogeneous. They are very different in their technologies, in their infrastructure, in their even consensus mechanisms. So saying that, it means we cannot use the native verification method for our breach. Also, we are not going to use external verification because in that case we cannot achieve the trustlessness. So based on these assumptions, we have chosen the atomic swap mechanism as a base technology for our breach, and further we can see how it works. So what is atomic swap? Atomic swap is actually a peer-to-peer protocol that eliminates the need of third-party mediation. And it's called atomic because the process either happens completely or doesn't happen at all. It cannot stop halfway. So consider this scenario when Alice on the left wants to exchange her Ether token for Bitcoin with Bob. And there is a problem. Who goes first? For example, if Alice sends funds to Bob, there is no guarantee that Bob will send his funds in exchange. What's the solution? So obvious solution is to use interactive escrow accounts that will eliminate the situation when any of the party holds both currencies at the same time. So what we will do? Both Alice and Bob send their funds to the escrow accounts. Once the funds are delivered and both escrow accounts informs each other about that, they will send funds back to recipients. So the process is completed, no harm, no foul. Imagine the scenario when only Alice sends her funds to the escrow account and Bob doesn't. So in that case, after some predefined time, the funds will be just refunded to Alice. Again, there is no problem. However, in this scam, there is a custodial risk of using escrow accounts because anyhow we need to trust this service in order to use it. In order to eliminate this risk, usually the HTLC protocol is used. HTLC protocol stands for hash time lock contract, and this is actually a time-bound conditional payment protocol that can eliminate the risk of third party and can automate the whole process. And the main principle of this protocol is introducing a special type of transaction, which is called HTLC again. And it has two properties. First is a hash lock. That means like two-factor authentication, that recipient, in order to claim the funds, need to provide a secret phrase or code. Another property is time lock. That means, again, that in order to claim the fund, the recipient need to do that inside this time period. If this period expires, the recipient cannot claim the funds anymore, but the original user can refund back his funds even without providing a secret. So in this example, Alice and Bob again want to exchange their funds, and both create HTLC transaction. So the difference with atomic swap is that both put hash lock and the time lock on the escrows. After that, in order to claim the funds, Alice needs to provide the secret to Bob. And the obvious way to do that is using just communication channel, for example, Telegram or something else. The same can do the Bob. After the secret is revealed, both users can use it to claim the funds, and the escrows send it back. That's it. Okay, now we are ready to consider how the HTLC protocol can be used in a cross-chain atomic swap in a EURS breach. Here we have two chains, A and B, and we have a user that has wallets on both chains. On the right side, we have a breach who also has each wallets on breach A and B, which is called pool. According to the HTLC protocol, the user first comes up with a secret phrase. And first, he creates a hash and creates a HTLC transaction on the chain A and puts his funds there. The breach cannot use the output of this transaction because he doesn't know the secret. So what he needs to do is to create a second HTLC transaction on chain B with the same amount of tokens using the same hash as was used in the first transaction. At this point, this is a moment when the user can change his mind. If he changes his mind and wait for some time period, which is defined by a time lock, the funds will go back to user and the bridge. But if he does not change his mind, he will create a redeem transaction. For that, he will use the secret, and because the hash on the second transaction was the same from this secret, the funds can be claimed by the user. After that, the secret is revealed on chain in the transaction, and the bridge, seeing that the transaction is done, will subtract the secret from the transaction and use it to create a redeem transaction on chain A. By this, the process has finished and both parties received their funds. Do you see any problem here? May I ask you, do you think that the time period for the first HTLC transaction and the second HTLC transaction that made by bridge is the same or different? Please raise your hand who thinks that the time period is the same. Nobody. So everyone else thinks that they are different. And you are right, because if we use the same time period, there could be a situation when user already claimed his funds, but the bridge doesn't have time to claim his part of funds. And that's a problem. Okay, let's finish. And here is an example of architecture, the high-level architecture of the bridge. And let me say that all the logic of creating the HTLC transactions and verification is put on escrow smart contracts on both chains. The bridge agent acts as a mediator and the communication channel between the chains. But he doesn't implement any centralization point here because of nature of the protocol. It just helps to move the transaction to its final stage. He cannot interfere, he cannot change the flow. He can only deliver messages between the chains, and it does through the blockchain infrastructure layer, which is abstraction over the underlayer protocols. And for the end user, there is a Swap Web UI that is used for actual operation. So in the conclusion, I would say that blockchain bridges and blockchains is a very big topic, and there is no single good or right solution when it comes to design of bridges. And here I just gave an example of implementation because every time is a trade-off under given initial conditions. I'm ready to answer your questions.
Thank you for an interesting speech. Could you elaborate more on what is bridge agent? I mean, is it a company? Is it a web service? What is their business model? Do they earn money on commission? What the point of their existence?
Okay, thank you for the question. Of course, this is not an operator or a human being or any company, organization. This is a software service that performs communication functions. In order to put more decentralization in a bridge architecture, usually those components is done as a network, not just a single entity, but a network of nodes that ensure that a bridge functions is available anytime. Because if for some reason this relayer is not available at a moment that he needs to deliver messages, the bridge will not function.
So do they earn commission on this?
Of course, every bridge usually takes some commissions because also the bridge perform some transactions, and transactions consume gas, consume some money. So it needs to be covered anyway.
Hi, Dmitry. I would like to ask about this time frame, actually this in HTLC protocol. So usually, I just want to know the difference between initial time frame and the second one that breach use usually. So how lower it is? 25, 30% or?
Well, again, it depends on how we design our breach architecture. We need to allow enough time for a breach to make a second transaction. So it needs to be secure.
And how long usually this first time setting is put on the user?
Well, it can be 50% more or twice the time as the first time frame.
You mean less?
More.
More, so the breach needs more time.
Well, sorry, the breach needs the time frame for the second HTLC transaction is less than the first one.
Yeah, that's what I mean. So it's 50% less.
Yes.
Approximately. And the whole amount of time, usually how long it is? It's 1 hour?
From 1 hour to 6 hours or even more.
Okay, perfect. Thank you very much for answering.
Thank you. Is it widely used right now, this protocol, everywhere, or like or not everywhere and like not widely?
Well, this protocol was appeared actually several years ago, and there are already commercial bridges that use that concept. I can name some of them, for example, HOP protocol, Liquality bridge, Connext protocol. They all locally verified bridges, and they use such approach.
But there are other protocols that also used by other bridges, yes? Or
Of course, as we discussed, there are different approaches for the bridges. There are externally verified as the biggest group, and also natively verified, like, for example, Layer 0, very modern protocol. But they have limitations because they cannot provide extensibility. They can, for example, only bridge between EVM compatible networks, not everything.
Thank you.
How can end users of your system can have guarantees that you will have parity with euro? Because as we know, stablecoin sometimes just lost its parity, and there is some problems with it. How can you give us trust that it will not happen with you?
Right, thank you for the question. Actually, we need to understand the difference between stable coins, and there are basically two big types of stable coins. One is fiat-backed, and another one is algorithmic. When it's fiat-backed, then every token is equivalent to the fiat money, and those fiat money is usually put in a bank. A good example is the USDC token, for example, which is USD-backed. And for those companies, there is usually regular audits, financial audits, that verifies that the reserves that is stored on a bank is equivalent to the token liquidity on chain. So EURS token is fiat-backed, and we also have the verification audits. So that's a guarantee for the user that each euro is equivalent to the fiat euro. For the algorithmic stablecoins, there is no such verification procedure, and you probably remember the big hype in last year when one algorithmic stablecoin has dropped, and it influences a big alarm on the market.
Thank you. Dmitry, now it's time to choose the best question. Which one was the best?
Difficult choice. Okay. Probably the first question about the agent. I think it's more technical, and I think it's best.
All right, thank you so much.